Let's look at number 1 from Related Rates AP Review. This is a calculator problem. So oil is leaking from a pipeline on the surface of a lake and forms an oil slick whose volume is increasing at a constant rate of 2,000 cubic centimeters per minute. We see this volume increasing. This is not a static value. This is a changing value. Volume is increasing. We know time is involved, and we know this is going to be a related rates problem. So volume is V, but with respect to time, it's going to be dV dt. So, this value is increasing, so we want that to be a positive value. Okay, we'll gather that information and put off to the side. The oil slick takes the form of a right circular cylinder with both of its radius and height changing with time. Okay, and volume formula is given. So part A, at the instant when the radius of the oil slick is 100 centimeters, so we can go ahead and gather that information, put that down. Height is 0.5 centimeters. The radius is increasing at a rate of 2.5 centimeters per minute, so dr dt is 2.5 centimeters per minute. At this instant, what is the rate of change of the height of the oil slick? So we're looking for the rate of change of height, so we were looking for dh dt, right, here with respect to time. So that's our value that we're looking for. So let's look at all the information we've gathered. We know dr dt is 2.5, dv dt is 2,000. We have r, we have h, and we're looking for dh dt. The volume formula is pi r squared h. We can think of this as finding the derivative to get dv dt. But there are two variables here. Remember, pi is just a constant, so really the r and the h involved, which means that if we want to involve the derivative, we have to use product rule. So f prime times g plus f g prime. Remember, though, with related rates, every variable is going to have a d over dt as soon as we find its derivative, because the underlying variable that we don't see is time. Time is the independent variable. So v becomes dv dt. Pi r squared, we have to go through f prime, so pi stays, we do 2r dr dt, so 2 pi r dr dt. H is the original g function, pi r squared is the original f function, and then g prime is h's derivative, which is 1 dh dt. So now we have everything that we need. We can just put everything into our equation. So dv dt gets replaced with 2,000, r gets replaced with 100, dr dt is 2.5, h is 0.5. Here replace r with 100, and then that leaves us with the only variable that we need to solve for, and that's dh dt. And then we just multiply this out, subtract over, divide over, until we get to dh dt, and we see that the rate of change of the height of this cylindrical disk, this circular cylinder, is 0.039 centimeters per minute. Okay, part B, a recovery device arrives on scene and begins to remove oil. The rate at which oil is removed is r of t, where t is time in minutes since the device began working. Oil continues to leak at a rate of 2,000 cubic centimeters per minute. Find the time when the oil slick reaches its maximum volume. So here's what's happening is when this recovery device arrives, it's going to start sucking up this amount of oil per minute, but then the oil continues to leak. So the volume that is on the ground is changing at this rate that we call dv dt. So dv dt is going to be the rate at which it's going to be the sum, or the rather the difference of oil being added and then the oil being removed. And whatever the result of this is going to be the rate of change of that volume on that oil slick. So this is our formula here, where 2,000 represents the amount of oil that's being added to the oil slick, and then R of t is the rate at which it's being removed. Then we know the maximum volume is going to occur whenever this rate is equal to 0. So we can set dV dt equal to 0, and then we can solve for RT. Sorry, we can solve for T. We can replace R of T with 400 square root of T. And then we can solve for T. So divide by 400, square both sides, we get T equals 25. So just to confirm, we can put dV dt on our sine line, dV dt sine line, with 25 as our T value. We can test 1, we can test 26 into dV dt, and we're going to see a volume that is rate of change is increasing until it hits 25, and then at time t equals 25, this rate of removal is going to eventually get up to speed where it's going to start sucking up more oil than what's being added, so that oil slick is going to start decreasing after 25. So oil slick is going to reach a maximum volume since dV dt changes from positive to negative at 25. Okay, part C. By the time recovery device began removing oil, 60,000 cubic centimeters of oil had already leaked. Write but do not evaluate an expression involving an integral that gives the volume of oil at time t found in part B. So there's three things we have to keep track of if we want to discover an expression for the total amount of oil for that oil slick. The total amount is going to depend on how much is there at the beginning, which we're told is 60,000. How much oil has been added because of the leak from the pipeline. So the integral, we know it's going to be 2,000 cubic centimeters per minute. So if we integrate, anti-differentiate that rate, then we're going to get the total amount being added. And then the total amount being removed is the anti-differentiation of that rate from 0 to 25. So the total amount is going to depend on the initial plus the amount created by the oil leak minus the device that's sucking up that oil.